In this lecture, we want to take another look at complexity analysis and do some examples to help you understand how this all works. We want you to develop an intuitive sense of what the complexity classes mean and how algorithms are assigned to those complexity classes. So I essentially right now want to work a number of different examples and look at the process. So first I'm going to switch to the sketch pad. It's easier to work with. Recall that we have 5 symbols we're going to use. Big O, little o, theta, big omega, and little omega. Big omega means the set of functions that grow at a rate equal to or more slowly than our candidate function. So graphing in here, big O of n. Big O of n represents the set of functions that grow at a rate equal to or more slowly than n. Therefore, if we shade this region, we can see this is the set of functions that grow at a rate big O of n. So, for instance, is it true that log base 2 of n is equal to big O of n? Another way we might write this, though using the equal sign is the most common, we might write this as log base 2 of n is a member of the set of functions, big O of n. Both of those are valid, though this way is in fact more common. Is this true? What you want to do then is graph your candidate function into what you have already done with the complexity classes, see where it falls. Is log base 2 of n inside the shaded region? Yes, it is. Therefore, this is true. Now, what about n squared? Is n squared equal to big O of n? N squared, of course, graphing that is here. It is not in the shaded region, therefore, no, this is not true. N squared is not in the set of classes represented by big O of n. All right, I want to look at each of these 5 functions then in turn, taking the other 4. I'm going to clear the sketch pad now. Little o of n. Little o of n. This is the set of functions that grows at a rate strictly slower than n. These are faster functions. Since we're not including the line, I'm going to make it dashed here. The line is not included. And then shading the set of functions, little o of n, we have everything that is below the line. So for instance, is it true that n equals little o of n? No, this is not true. It is not in the shaded region. The line is not included. N squared equals little o of n. Again, this is false. N squared is not in the shaded region. Log base 2 of n is equal to little o of n. This is true. Log base 2 of n is down here. It is in the shaded region. So little o of n means the set of functions that grow at a rate slower than n. Our next complexity class is theta. And theta means it grows at exactly the same rate. F is in theta of g if and only if they grow at precisely the same rate. So when we graph this function, theta of n, Is it true then that n squared equals theta of n? No, this is false. It does not grow at precisely the same rate. Similarly, is log base 2 of n equal to theta of n? Also false. They do not grow at the same rate. 2n equals theta of n. This is true. 2n and n grow at precisely the same rate. So theta then is the tightest bound. It means it grows at precisely that rate. Our next symbol is big omega. And this is the set of functions that grow at a rate faster than or equal to n. That is, these are all functions that are equal to or worse than n. Worse than meaning they grow at a faster rate, they take more time. So that is the set of functions here that are on or above the line. So, is it true that n is equal to big omega of n? Yes, this is true. It is on the line, therefore it is true. Log of n is equal to big omega of n. This is false. It is not in the shaded region. The log function grows at a rate slower than n, therefore it does not grow at a rate equal to or faster than n. N squared is equal to big omega of n. This is true. If we graph n squared, as we can see, it is in the shaded region. It is a member of that complexity class. The final symbol we want to look at is little omega of n. This is the set of functions that grow at a rate strictly faster than n. These are algorithms that are worse than n. These are algorithms that are slower than n. We're going to use the dashed line again to indicate that it is not included in this complexity class. This is the set of functions that grow at a rate strictly faster than n. They are algorithms that are slower than n or worse than n. So for instance, is n squared equal to little omega of n? Yes, it is. This is true. It is in the set of functions that grow at a faster rate than n. N squared grows at a faster rate than n, therefore this is true. It is in that complexity class. N to the fifth equals little omega of n. Again, this is true. Some constant c to the n is equal to little omega of n. Exponential functions are worse than any polynomial bounded functions. Therefore, this is also true. Log base 2 of n is equal to little omega of n. This is false. This is false because the log function down here is not in the shaded region. It grows at a slower rate than n. Therefore, it's not strictly worse than or grows at a faster rate than n. So these are the 5 symbols that we are working with. You may wonder why we have 5 symbols. Why do we need these? Well, this is really to give us the tools we need to describe a wide variety of algorithms in a meaningful way. So as an example, I want to consider again big omega. In this case, big omega of n log n. This is the set of functions that grow at a rate equal to or faster than n log n. So for instance, can we put n squared into this class? Does this work? Yes, it does. So this is bounded from the other direction. N log n is worse than n, but not as bad as n squared. So let's draw a function here, n log n. And big omega is everything that is on or above the line. This is the set of functions that grow at a rate equal to or worse than n log n. It turns out that this is a very useful complexity class because we can develop a proof that says any sorting algorithm that compares two elements in an array cannot be better than n log n. That is to say, any sort algorithm that compares two elements is going to be at least as bad as n log n. It might be worse, but it can't be any better. Therefore, every sort algorithm known that compares two elements must be in this shaded region. This is an example of bounding from below. This is an example of the worst case scenario. In this case, when sorting, we say that the best it can be is n log n. It can't be any better than n log n. So that is our bound. More commonly, we use big O. So we'll use another sort algorithm as an example. There is an algorithm that we will study later in this course called insertion sort. And this algorithm has interesting behavior. That is, the average and worst cases are n squared. The average and worst cases are n squared, but the best case is n. That is, in the best case, you have an array that is already in sorted order. And if you used insertion sort on such an array, then the runtime will be n, not n squared. Therefore, this algorithm has two different complexities. One complexity for the best case, another complexity for the worst and average case. Therefore, we're going to say this algorithm is equal to big O of n squared. What this means is it could be as bad as n squared. It might be better, but it won't be worse. The worst case is n squared, but it might be down here somewhere. Now, it would be incorrect to say this algorithm is equal to theta of n squared. This is not true. This is not true because it's not exactly n squared. It might be faster. In the case of an already sorted array, it is faster. Hence, we want to bound this on the top here. The insertion sort may take as long as n squared, but it might be better. Therefore, we need to have less precision here. Theta of n squared is an incorrect answer. Now, I want to extend this a minute and suggest another problem to you that I want you to think about. Suppose the problem is to find the elements find a specific element in an unordered array. So you have something like private int find int x. So with this function, what it does is it looks through the array to see if x exists. If x exists, it returns the index where x is. If it doesn't exist, it will return a -1, which of course is an impossible index. So that's the not found condition. The array is not in order. So if the element is in the array, how many elements are you going to look at? How many comparisons will you make between x and an element in the array before you either find it or determine that it's not in the array? In this case, it's possible that you might find what you're looking for at index 0. However, this is a specific instance and is not terribly useful. On average, we would expect to go maybe n over 2 times that many comparisons if we're searching for an element in an unordered array. And so since this is the case, is it better to say big O of n instead of theta of n? Put another way, are both of these correct? Is this exactly n? Is this exactly n? Does it fit into the complexity class theta of n? Even though there exists the possibility that we might go to the first element array of the array and find it there. Well, to find out, we have to take the limit as n goes to infinity, and the average case of this is n over 2 over n, and so this is going to resolve to a constant. It's 1/2. Therefore, they grow at the same rate. In other words, both of these are correct. This is a single instance that we can throw out. It's really not important. That is, we don't care what happens with a single specific instance. Similarly, we looked earlier at binary search. It could be the case that when you search for the array, you go to the middle of the array and immediately find what you're looking for, and it's taken one comparison. Well, is it true to say that binary search in the best case is big O of 1? No, it is not correct to say that, because we're talking about a very specific instance. What we're looking at with the complexity class is the amortized behavior over an extended period of time. Now, I just spoke of the specific case of insertion sort, where the best case, if the array is already sorted, that this is big O of n. Isn't that a specific case? And it is not, because it applies to every sorted array. The next example I want to talk about, suppose we have private int find min. This is a function that searches an unsorted array and identifies the smallest element in the array. Now, if you stop and think about the work that needs to be done in this case, you will see that you have to examine every single element in the array. You have to do exactly n comparisons to find the smallest element. In other words, you must do exactly and precisely n compares. Well, let me revise that. The truth is it's exactly n minus 1. N minus 1 because you take the first one as the minimum and then compare it to every other element in the array. So you have exactly n minus 1 compares. In terms of complexity, n and n minus 1 are the same thing. So my question now is it correct to say that this algorithm is in big O of n, in theta of n? Are both correct? Is one better than the other? After all, we are doing precisely n minus 1 comparisons. Therefore, would it be better and more correct to pick theta of n over big O of n? And the answer is no. No, that's not true. They're both correct. They're both absolutely correct. The big O of n says the function grows at a rate equal to or faster than n. This one says it grows at a rate equal to n. Well, it does grow at equal to n. The problem that students encounter sometimes is they believe that this answer is more correct because it indicates exactly n. But that's not true. The complexity classes never indicate exactly n. What they indicate is that it grows at a rate exactly equal to n. So, is this true? N over 1,000 equals theta of n. Yes, this is absolutely true. Okay, what about 50n plus 1,000 n over 2 plus 10 equals theta of n? Is that true? Yes, it is. It grows at precisely the same rate as n. And you know this because you can take the limit. You take the limit of this function over n, therefore, it grows at the same rate. So here we have an algorithm that prints a message a certain number of times. So we have for int I equals 0, I less than n over 2. And then the second loop is I less than n over 4. The third loop, I less than n over 8. What is the complexity of this algorithm? So let's take a look at this and see. These are sequential loops. They're not nested. They're one after the other. So we do n over 2 steps plus n over 4 steps plus n over 8 steps. And so this is equal to for n over 8 plus 2n over 8 plus n over 8 is equal to 7n over 8. Okay, so what complexity is this? 7n over 8. Is this equal to big O of n? Yes, it is. Throw away coefficients. Therefore, you have n is equal to big O of n. This is true. Taking the limit, 7/8 is actually 0.875. So if we take the limit of 0.875 n over n, as n goes to infinity, we get 0.875. And this is a constant not equals to 0, which means they grow at the exact same rate. So yes, it is true that 7n over 8 is equal to big O of n. It is also true that 7n over 8 is equal to theta of n. I have a chart here that shows the number of times the message prints. So you'll notice we double n each time. We go from 10 to 20 to 40 to 80. And the number of times it prints also doubles. Now it's true that 8 times 2 is not equal to 17. However, an off by 1 doesn't really matter. But from that point, it does double. 35 times 2 is 70, times 2 is 140, times 2 is 180. So it grows exactly at the rate equal to n. Now here I have another code sample, and we have 3 different segments here. That is, these aren't intended to run sequential. Rather, there are 3 variations of the same problem. Notice here that the stopping condition is the same for all of them. That is, start at n, stop or keep going as long as I is greater than 0. But the final part of the for loop, we have I is equal to I divided by 2, I is equal to I divided by 3, and then the last one, I is equal to I divided by 10. I hope that you can recognize that this is log n. So imagine that for the first example, I is 1,000. The first pass of the loop, we start out with I is equal to n, and n is 1,000. The next pass of the loop, we have I is equal to I divided by 2. So the values for I, as this loop runs, is 1,000, 500, 250, 125, and so on. It's cut in half every time. This is log base 2 of n. The second example, if we start out with I is equal to n, and then the next pass of the loop, I is divided by 3. So 1,000 divided by 3. This is also log n. Recall that all logs are created equal. Finally, the last one, we start with I is equal to 1,000, and then I is 100, and then I is 10, and then I is 1, and then I is 0, and the loop stops. So these are the results for I divided by 2. So we go 10, 20, 40, 80, doubling in each time. Notice that the times that the message prints is one more when we double the input size. Therefore, the number of times the message prints doesn't double, it increases by 1 when we double in. This is log behavior. With log base 10 of n, we have a situation where it appears to grow more slowly, yet it grows at the same rate. Therefore, all logs, again, are created equal. This is such an important idea that I want to look again at this example and an example of solving complexity involving a log. So we know that log base 2 of n and log base 10 of n grow at the same rate if the ratio as n goes to infinity of log base 2 of n over log base 10 of n is equal to some constant. If this statement is true, then they must grow at the same rate. So we can take this ratio, we can take this limit, and see what we get. So we can start first with an identity. The natural log of n or the natural log of 2 over ln of n over ln of 10. We're taking the limit, of course. Simplifying, then, we can flip and multiply, so we have ln of n over ln of 2 times ln of 10 over ln of n. Now canceling, we have ln of 10 over ln of 2. And this resolves to approximately 3.32. It's a constant not equal to 0. Therefore, it is true that they grow at the same rate. Now we have another example here, and these are nested loops. So for int I equals 0, I less than n, I plus plus. The nested loop, int j equals 0, j less than I. Notice that j is not less than n, but j is less than I. And then the third nested loop with k, we have k less than j. Now in the case where we have nested loops, but the inner loops are not dependent on the input size n, then you don't count them. That is to say, if we have 3 nested loops with n, then they're n cubed. However, if they're not dependent on the input size, then you don't count them. For instance, looking at the example here, suppose with the most inner loop, the k loop, we said for int k equals 0, k less than 10, k plus plus, then this algorithm would be n squared. We would not count the k loop at all. But this algorithm is in fact big O of n cubed. Why, you may ask? Because k less than j, what does that have to do with the input size? Well, in fact, the number of times I runs depends on n. Therefore, for the second loop, int j equals 0, the number of times the j loop runs depends on I, which depends on n. And the third loop, k depends on j, and j depends on I, and I depends on n. Therefore, all 3 of them will increase as the input size increases. Therefore, this is an n cubed algorithm. And here are the number of times the message prints, and as you can see, as we double the input size, In fact, this is n cubed behavior. The next one, this example also has a log, and it turns out that logs are fairly common in complexity and you need to know how to handle them. So I want to do one more example here using the logs. Recall that if we want to determine whether or not this statement is true, is n to the 1.5 or n to the 1.5 or n to the 3 halves, is it equal to big O of n log n? True or false? We can determine this by taking the limit of the ratio. So I'm switching over again to the sketch pad to do this. So n to the 1.5 is actually n times the square root of n is equal to big O of n log n. So we want to know if this statement is true or false. All right, first of all, what's the growth rate of n times the square root of n? This is n to the 1.5. It is in between n and n squared. But where is this function? Also in between n and n squared. Therefore, both of these functions are in between n and n squared. But do they grow at the same rate? Is one faster than the other? So to answer this question, we must take the limit of the ratio. So the limit as n goes to infinity of n times the square root of n over n log n. Well, we can do an immediate simplification here, getting rid of an n, the square root of n over log n. So, how does this ratio compare? Do these grow at the same rate? Is one faster than another? We know from L'Hopital's rule that we can take the limit of the derivative of these two. So we can do that, dn square root of n over dn log n, the limit as n goes to infinity. Now we want to do this because it will get rid of the log. This will turn into 1 over n. And again, this is L'Hopital's rule, which you should remember from your calculus class. All right, so we need to take the derivatives here, and we can do this easily. So we have 1 over 2 times the square root of n over 1 over n. So this is equal to 1 over 2 times the square root of n times n over 1, and this is equal to infinity as n goes to infinity. That is the limit of n over the square root of n as n goes to infinity. This totally dominates. Therefore, n times the square root of n is not equal to big O of n log n. Is it true that n times the square root of n is equal to big omega of n log n? And yes, this is true. It grows at a rate faster than n log n. Therefore, it is in the set of functions bounded by n log n. So if this function is n log n, then n to the 1 1/2, or n times the square root of n, is within the shaded region. So yes, this is true. I want to now do some additional examples here. So these are all true or false questions. N log base 10 times n is equal to theta in log n. True or false? Notice that we have not put a subscript on the log inside the complexity class. This is not done because all logs are equal. Yes, this is true. It would also be considered big O of n log n, but it's also correct to say that it's theta of n, which means they grow at exactly the same rate. So 1 million n is equal to theta of n. True or false? Well, if we take the limit of the ratio, 1,000 n over n, or I'm sorry, 1 million n over n, as n goes to infinity, the limit is 1 million. It's a constant. Yes, this is true. 3n squared plus 5n cubed plus 25n is equal to big O of n cubed. True or false? Again, this is true. What we're going to do is we're going to throw away all of the lower order terms and all of the constants and coefficients. We're left with n cubed is equal to big O of n cubed, and yes, this is true. 17n cubed plus 25n squared plus 7 is equal to big O of n to the fifth. Is this true or is it false? Now I want to add, this is a tricky question. Now I put it up here on purpose because what does big O mean? Big O means the set of functions that grow at a rate equal to or more slowly than n to the fifth. Is it also true that this function is equal to big O of n cubed? Yes, it is. That's also true. This is a tighter bound, and this is the preferred answer. But is this one wrong? No, this is a true statement. Now recall from the principles we gave you that when you're adding two complexity classes, you take the max of the two. Therefore, if we said this is equal to theta of n to the fifth, this would be false. It's not true. It does not grow at exactly that rate. We could, however, say that this is equal to theta of n cubed, and this is true. This is true. Therefore, this is somewhat of a tricky question. However, if we alert you to these and point them out before they appear on a test, they cease to be tricky questions. But it's important to understand that this is the function, the set of functions that grows at a rate n to the fifth or more slowly. All right, let's clear our pad here and move on to the next problem. N times n minus 1 over 2 is equal to n squared. Is that true? Yes, it's true. We have n squared minus n over 2. You throw away the minus n, you throw away the over 2, and it's true. All right, let me change this for a moment. And instead of n squared, we make this n cubed. Is it still true? Yes, it is still true. It is still true. All right, is it true that this is equal to theta of n squared? Now again, this sometimes baffles students. They say, now wait a minute, n squared minus n over 2, that's not equal to n squared. Well, of course they're not equal. The question is it a member of the set of functions that grow at a rate equal to n squared? In other words, does the function n times n minus 1 over 2 grow at the same rate as n squared? And the answer is yes, it does. You can take the limit and easily see that it does. 25c equals big O of 1. Is that true or false? Well, if we use n as the input size, then there is no input size on the left-hand side. And in fact, this function does the same amount of work no matter what n might be. If n is 100, how many times does 25c go? Well, it goes a set number of times, but does that number of times change if n increases to, say, 1 million? No, it does not, because this is not dependent on the input size. Therefore, this is true. 25c to the n is equal to big O of n. Is this true or false? This is false. This is false because exponential functions grow at a faster rate than any polynomial bounded function. If we take the limit of 25c to the n over n, we get infinity. Therefore, this grows at a much faster rate. 25c to the n is equal to big omega of 2 to the n. Is this true? Yes, it grows at a rate equal to or faster than 2 to the n. So yes, this is true. The next problem. N plus 1 equals big O of n. Yes, this is true. This one should be obvious. This is true. 2n squared equals big omega of n. Is this true? Yes, this is true because big omega of n is the set of functions that grow at a faster rate than n. In other words, if we graph this, n, does n squared fall on the shaded area? The set of functions that will grow at a rate equal to or faster than n are here. Is n squared in the shaded region? Yes, it is. Therefore, in fact, it's true. Finally, I want to use a metaphor, an analogy, to call your attention to some important aspects of all of this. So I want to tell you a little story. A few years back, I went back to the Midwest for a family reunion. There were going to be a lot of people coming to this reunion, and they were coming from distances, so they weren't bringing food, which meant that my sister, who was hosting, was responsible for making all the food. Feeling guilty, I went into the kitchen and asked if I could help her. And she said, yes, certainly you can. You can peel some potatoes. So I sat down at the table and I began peeling potatoes. And my sister came by in a little while to check on me, and she noticed that I was making very little progress on this mound of potatoes, and she said, Alan, I'm going to have to help you. We need to get these done. So she grabbed a chair and sat down and started peeling potatoes. Well, I noticed that she could peel about 4 potatoes in the time it took me to peel 1. So if we look at the times here, we make a little chart. We have number of potatoes. And of course, this is the problem size. This is n. And then we have the time it takes. All right, for me, I could do, say, 1 potato in 1 minute. However, my sister could do 1 potato in about 15 seconds. In other words, she peeled about 4 potatoes for every one that I was able to do. Okay, so we're talking about complexity here. So Alan does n, and Alan's sister does 4n. Much faster. That is to say, is n equal to 4n? Well, of course not. N is not equal to 4n. And if we were to graph this, you would see something like in and then 4n. Not a very good artist, but you get the idea. And the reality is, the further down you go, as n increases to infinity, the gap between n and 4n grows. This gets wider and wider and wider. But with complexity analysis, we say that they're the same. That is, n is equal to big O of n. 4n is equal to big O of n. Therefore, n and 4n are the same. Well, what does that mean? What we mean is that they grow at the same rate. They grow at precisely the same rate. This is quite different from saying that they're the same, because they are not. This is an important distinction that I want to point out, and this is kind of the difference between software and hardware. So if we use the computer analogy, then my sister has a faster CPU. She's 4 times faster than I am. Well, what we're timing when we get the actual times here, 1 minute versus 15 seconds, that has the influence of the hardware in it. So the computer's faster, but the algorithm is not. The potato peeling algorithm, whether implemented by my sister or by me, is exactly the same. It is the same efficiency. It is the same complexity. In fact, suppose that someone were to invent an automatic potato peeler. Someone probably has. I've never seen such a device. But imagine that it worked like this. You drop this potato into the potato peeler, and it secures the potato, and then it runs a blade along the surface of the potato until it cuts off all of the peels. Again, this might be much faster than even my sister, but it's the same speed, because if you double the number of potatoes, it's going to take twice as long. So any algorithm that works with this methodology, that is, you take the potato and slice off all of the peels, they will grow at precisely the same rate. The algorithm is the same, even though there might be a very wide difference between the amount of time it takes me versus my sister versus an automatic peeler to get the same job done. But the algorithm is taking a potato, slicing off the peels. No matter who's doing it, the algorithm is the same. So to contrast this, let's look at a faster algorithm for actually peeling potatoes. Years ago, when I was a child, we lived on a farm and we grew our own vegetables. So we had a root cellar, and in the cellar were lots of potatoes. And when we dug them up and harvested the potatoes, they were all different sizes. They didn't come with approximately the same size as they do at the grocery store. So some of the potatoes were quite large and others were very small. In fact, a number of them were the size of marbles or golf balls. At one point, my mother asked my older brother to go down into the root cellar and get some potatoes because we were going to have mashed potatoes for dinner. So my brother, being mischievous, went down to the cellar and he sorted through all of those potatoes and picked the smallest ones he could find. So he brought back a bowl full of potatoes that were the size of marbles, some the size of golf balls, but none larger than that. My mother looked at those potatoes and immediately thought, I suppose, of punishing him, but my grandmother said, "Oh, don't worry about it." She took all those potatoes and dumped them into a pot of boiling water, did not bother peeling them at all. Then when they were cooked, she dumped them into a food mill, a couple of quick turns of the crank, and that pushed all of the potato through the food mill, leaving the peels behind. Right, this is a faster algorithm, because there might have been 50 or 80 potatoes in that bowl that were cooked and they went into the food mill. But it doesn't matter what the actual count of the potatoes was. They all took the same amount of time. My grandmother cranked the food mill and out came the potatoes minus the peels. That's a faster algorithm. Now, does it matter that my sister could peel potatoes faster than I can peel them? Well, of course, speed always matters. Is for n faster than n? Sure it is. Of course it is. But is the algorithm faster? No, it's exactly the same. It grows at the same rate. If you double n, it takes twice as long, no matter how long any specific instance of n takes.